Hey folks, welcome to CSE 1322. This is lecture number 22, and today we're going to pick up where we left off in the last lecture where we were talking about linked lists, and we're going to extrapolate this out into a bigger structure such as a stack or a queue. So as a quick review, in the last lecture we spoke about a linked list as being a set of nodes that each knew how to get to the next node or were linked to the next node. It's a dynamic data structure that can grow and shrink. So a couple of applications that we can talk about for dealing with or for using a linked list would be a stack or a queue. These are common situations in computer science, in software engineering, in game design, and IT, where you have a set of instructions or a set of things that need to happen, and you want them to either happen in one order or a different order, and we're going to talk about the two different ways of doing stuff from stacks and queues. So the first thing I want you to think about when we're talking about a stack is I want you to think about some pancakes. And if that doesn't get you hungry, I don't know what will. But anyway, so lovely drawing here on wherever the heck I found this, Etsy. All right, so pancakes indeed are an implementation of a stack. When you cook pancakes, if you've ever actually cooked pancakes, you mix up the batter, you warm up a frying pan, you throw some of the batter on the frying pan, it makes a pancake. You take it out and you put it on a plate. The first pancake that you make is going to be the pancake that is at the bottom of the plate. The next pancake that you make is going to be the one above it, and then the one above that, and then the one above that, and then the one above that. But when you eat them, you're actually going to eat them from the top down. So very strangely, the first pancake that you're going to eat is actually the last pancake that gets made. Unless you're a barbarian and you cut your way through all of the pancakes, eat it like it's some terrible type of sandwich, in which case you're a terrible person and I can't have you watching this video anymore. But normal people eat the first pancake, the one that's at the top, which is how stacks work. So this is an example of a first in, last out data structure. The first pancake that's put in is going to be the last pancake that's taken out. Whereas a different structure, which is what's called a queue that we're going to talk about later, is a first in, first out data structure, and we're going to talk about that separately. So it's important that you remember pancakes when you're talking about stacks because they do call this a stack of pancakes, as you probably are aware. And so the first one goes on the bottom, and then you work your way up to the top, and the first one that you eat is the last one that's put on. So last in, first out. Stack. All right. So now that you have that in your head, let's do the quick review of linked lists. So in linked lists, we talked about a node. A node was a class that had at least two attributes. One of the attributes was the thing that you're trying to store in the node, which in the example that we did in the last class was an integer. And the second thing was the next, which was the link that gets you to the next node. So it's going to be of type node, and it is going to be called typically next, whereas the number that you're storing in there is going to be your data. All right, so the definition of a node, this is something that you might be asked to write on a test question, would look something like this. You would have class node, you would have int data, and int of course could be a string if you were storing something else. You will always have something next, you will always have this pointer or this link that gets you to the next node, and so it will always be of the same type as what it is that you're defining right now. All right, the second question that might come up on a test related to the last lecture is write a method that sums up all the numbers held within a linked list and returns the sum. So you'd have to know what the link name is for the front of the list, and in order to do a sum across the linked list, you might do something like this. So you would take in the current node, which is the one that you're starting off with, and if that is equal to null, then you would return 0 because that means there's nothing in the list. Otherwise, you would return the current data plus a recursive call to current.next. That's the recursive way to do this. The iterative way to do it is over here. They both work. There's nothing wrong or correct about either one of them. There's nothing wrong about either one of them. They're both correct. And so same kind of idea. Sum is equal to 0, so you're calling s equals 0. While current is not equal to null, then you're going to add to the s the current data, and you're going to set current equal to current.next. And you're going to keep doing that while current is not null, and at the very end you're going to return s. So both of those are perfectly valid ways to write a sum of a linked list, which starts at the beginning, walks its way through all the nodes, and gets you out the data that you want. So that's an example of something we might ask you to do. We might ask you to calculate an average or calculate the minimum, find the min or the max in a linked list. Those are all common examples of things that you might have to do in a linked list, and they all pretty much work the same way. Okay, so back to our stacks. Stacks are a last in, first out behavior. The last thing that you put into the stack is the first thing that you're going to get out. Typically, when you're dealing with stacks, you're going to have a method called push, a method called pop, and perhaps a method called peek. All right, so with a stack, the data cannot be accessed in any way other than by the rules of the stack. The last thing that you put in is the thing that you're going to get back when you do a pop. The way that you put things in is called push, and that's going to get pushed down in the stack as more things get put on top of it. You're pushing down the stack. Pop means you're popping something off the stack, and the stack's going to pop up just a little bit. Peek allows you to see what's at the top of the stack, and that's a common thing that you're going to need to be able to do. Okay, so here is the code for a stack, and very specifically, I've gone ahead and stuck that into Replit for you. Here's the C# version of it, and this is just taking the code that's on the slide, putting it in, adding just a couple of little modifications to it. You can grab the URL. You could easily convert this over to Java. The only thing you'd have to do is change the lowercase strings into capital strings. Other than that, I believe it would work exactly the same. Obviously, console write line needs to get changed to system out print line. All right, so what's going on here? Well, first off, I defined my node class. And my node class has, in this case, 3 things in it. I'm storing an ID and a string in each of the nodes. Okay, so I had mentioned this when we talked about it in the last lecture, that it's perfectly reasonable for the nodes to have more than one thing in them. As a matter of fact, that's quite common. So if you had a linked list of students, for example, each student would have a name and a KSU ID, a net ID, an age, address, major, I don't know what else, is graduated, as a Boolean, and so on and so forth. So in this linked list that we are creating for our stack, what I'm doing is I'm storing an ID and a name in each of the nodes, and then I'm going to store a next pointer, which gets me to my next node. And then I have a constructor, which simply takes in an ID and a string, and it goes ahead and sets them for me. Probably be also good to set by default next equals null, just so that life is starting off clean and nice. All right, so my stack class down here, I'm going to start off with what I'm calling top. In the previous class, I frequently called this head, or I called it front. In this case, since we're thinking of it logically like it's an up-down thing, we tend to call it top. You absolutely could call it front or head, and it would work just the same. So this is my link to the front of the list. And so I'm calling it top, and I'm setting it equal to null when we start off so that there's nothing in there. I'm then creating a constructor, and that constructor simply sets top to null, so that's kind of doing the same thing. All right, if somebody calls peek, I'm simply going to return whatever the top ID is. Very simple. If you try to push something in there, then I'm going to make a new node, which is going to have the ID and the name that you gave me in it. I'm going to set the new node's next to point to the same place as the top, and the top to point to the new node. All right, so let's go over to our little whiteboard here, and we're going to start off, and we're going to say top, and I'll just draw it vertically so that you can see what's going on. So top currently points to a list that has 2 items in it. So this is 1 and and this is 2 John. All right, and so what we were trying to do was we were trying to put a new thing in. It created a new node. The new node inherently has a next, which gets initialized to null. We put in whatever it was that we were going to put in here. So 3 Jane. Apparently Jane looks like Tane. All right, there we go. And then we set the new node, which we called new node. We set the new node's next to point to the same place as top, and we changed top to point to the same place as new node. and that has the effect of linking it like so. So now you can see top points to the first node points to the second node points to the third node, and the last node has null. All right, so that is the most recent thing that was put in this node. It is the top of the stack. So if somebody called peak, it would return 3 because that was the integer that was in here. All right, and then pop. This means that they're asking for something back out of the list. We always know that pop is going to take something off the top of the list, so pop should be pretty easy. What we're going to do here is we are going to say we're going to retrieve the ID and the name out of the top node, and I'm just going to store them in new variables called ID and name. And then I'm going to set top equals top.next. So I stored the 3 and I stored the Jane, and then I said top equals top.next. Well, top.next, as you can see from this picture, is this right here. That's top next. And so what I'm doing is I'm setting top equals to top next, which means the top's going to point to the same place as top next. And once I erase where it used to point, you can see that the effect of that is that top now points to the list, and this other weird node that's out there is no longer pointed to by anybody because, well, it's just there. And so then I print out what I got back from the node. All right, so just to prove how this all works, I'm creating a new stack that will initialize it to nothing. I'm pushing in Enda, Fred, and Jane just like I did, and then I'm going to pop twice. The first time I pop, we would expect to see Jane because that was the last one put in, and the second time we pop, we would expect to see Fred because that was the one put in before it. And indeed, you do see exactly what you would expect. So this is the exact implementation of a stack in C# with a linked list as the underlying data structure. There is no rule that says that you have to implement a stack using a linked list. As a matter of fact, you could do it in a number of ways, and that's kind of what we're going to talk about here. So the rule of a stack is that you're going to add and remove from the same side of the data structure. And that's because, just like we saw with pancakes, the most recent one that you put in is the one that you're going to take out. So anytime you put one in, it's going on the top, and when you're taking it out, you're taking it out of the top. To be clear, you could have implemented it the other way in Bizarro World, where you put the first one and you always put new ones on the bottom. You lift up the entire stack and you put the new one on the bottom, and you eat from the bottom of the plate. Now, you can realize very quickly that that's bizarre, and it's actually a lot harder to do. You would never really want to eat the bottom pancake. You'd have to grab the pancake and pull it out. You'd be doing that terrible magic trick where you rip the tablecloth off the table and try to not knock over anything else. So it doesn't make sense to implement it where the bottom of the pancake stack is the one that you eat, and it's also where you put things. It's much harder to do it. It is a valid stack, however. Let me be clear. There's nothing magical about the rules that says that the top always has to be on top. It just means that wherever you put new things in, that has to be the same place you take things back out again. So you could absolutely implement a stack using a linked list. That's what we just did. And we did it where we implemented it such that we put new things at the front of the list and we removed new things from the back of the list. Sorry, we put new things at the front of the list and we removed things from the front of the list. So why did we choose to do that? In a linked list, couldn't we have done it at the back of the list? Because we've seen the code for doing that before. And what I mean by that is, so we had our original top, and it had whatever was in here. It was one Enda, and then we had our 2 John. All right, and so what I'm saying is I could have chosen that when I added in 3 Jane, I actually added her in at the bottom of the stack. And then when they did a pop, I could have removed her out of the bottom of the stack as well. So why did I not do that? Well, if you remember when we were doing the code for inserted back of list, it was just a little bit more work in order to get to the back of the list because I had to create some kind of temp connector or pointer. at the front, and then I had to say, is its next equal to null? No, it's not. Then update it to here. Is its next equal to null? Yes, it is. Okay, that's where I'm going to insert my new node, and I set the next equals to null. And in this case, that wouldn't have been that much more work because there was only 2 items in the stack. But if I could imagine a stack that had 1,000 items in it, then just this walking my way through the stack would have meant that I would have had to 1,000 times updated that temp pointer before I get to insert the new one. No matter how many items are in the stack or how big the stack might be, if I'm always putting in at the top like I did in this actual code, then it's always going to be one operation to stick it in at the top. And likewise, when I'm pulling it out, it's always going to be one operation to take it out. So push, as long as I'm doing it at the front, is one operation. Pop, as long as I'm doing it at the front, is one operation. But if I do it at the back, at the bottom of the list, then it's much worse. The push operation is going to mean it's going to take me n updates in order to find the end of the list, n being however many items are already in the stack. So if the stack has 1,000 things, then it's going to take 1,000 operations. If the stack has 1,000,000 things, it's going to take 1,000,000 operations. And likewise for pop. So there's no good reason with a linked list to do it this way. It's just a lot more work, and there's no benefit to it, and it's just awkward. And when we think about the stack of pancakes, it's just awkward to eat the bottom one first. So why are you doing it? It's not character building. It's not making you a better person. Just put them in on the top and take them out on the top if you're dealing with a linked list. It's just so much easier. All right, so if that's the case, then is a linked list the only way or the best way that you can implement a stack? And the answer to that question is no, it's not the only way. We could absolutely do a stack with an array. Okay, so let's go back and think about an array. So let's imagine that I define an array and I say it has 10 cells. All right, and then in the first cell I put in 1 Enda, and in the second cell I'm going to put in 2 John. And then when I go to put in my next person, I'm going to put in 3 Jane. And then when I take somebody out, I'm just going to remove them out of this cell. And you get returned 3 Jane. Okay, so if I do it in an array, then I would always insert and remove from the end of the array. I certainly could do it from the beginning of the array, but I think you see the problem with that. If I do it from the front of the array and I always remove out of cell 0, then I'm going to have to shuffle everybody else in the array over 1 in order to make it so cell 0 is the beginning of my array. So that's not the greatest implementation. Putting it in and taking it out at the back of the array is much, much easier. So how would we go about doing this? Well, you would start off with an empty array, and you have your 10 cells. So you define an array. That might be one too many, I don't know. You define your array as you normally would, and each of the cells has their numbers like they typically do. Hey, I got it right, look at me. All right, so how do you insert? Well, you would keep track of a variable in addition to your array, so this might be my stack, which is an array. In addition to that, I would have current entries. And I'm going to initially set current entries equal to 0. All right, so when I go to put a new item in, if I'm doing a push, I'm always going to push it into the position in the array that is the current entries. Why? Because it's going to tell me where I need to stick the new person. So at the moment, current entries is 0. I'm being asked to push 1, Enda. All right, so what I'm going to do is I'm going to look up current entries. I'm going to see that it's currently 0, and I'm going to write into my stack at position current entries 1 Enda. Then I'm going to update current entries to be equal to 1. I'm going to increment it, add 1 to it. So now when I get called again, and this time I'm being asked to do 2 and John, I follow the same code. I look at the current value of current entries, which is currently 1, goodness, I can't get the eraser to work. Um, and then I insert the new entry, John, into my stack at position 1. So 2 John. I update current entries to be current entries plus 1, and I can keep doing these inserts all day long. So when you ask me to insert 3 Jane, oh, that was so cheaty, but there you go. When I insert Jane in, I do the same thing. I put it in the position of current entries, and life is good. So when you ask me to, and I update current entries to 3. So when you ask me to remove or to pop something out of the stack, all I have to do is look at current entries, subtract 1 from it, because current entries tells me how many things are currently in there, which you can see there are 3 items currently in there, which is why it's 3. But the last one is in cell number 2, because of course the array is indexed from 0. So if I subtract 1 from current entries, then that tells me I need to look in cell number 2. I'm going to take out the information that's in there, and I'm going to decrement this back down to a 2 because I have removed an item out of my stack. And now life is good. The only downside to this implementation versus doing it with a linked list is that I have a static size. I can only have 10 things in my stack. If you ask me to insert an 11th thing, I'm going to have what's called a stack overflow, because I will get past the end of the data structure that I created in order to hold my stack. So it's important that if you decide to do an array, that you make the array big enough to hold the maximum size you could ever possibly want the array to be. The other alternative is when you go to insert, or to push, if you notice that you're trying to push into the last cell, at that moment you can make an array which is double the size of the current one, copy all the data over into the new array, and then now you can grow again. And that means that it doesn't ever stop you from inserting stuff into the data structure. It's just that every time that you reach the end of the currently allocated size of the array, you're going to have to take this time to go build this new array that's double the size, and you put all the stuff back in. Why double? Why not just plus 1? Well, because it's a lot of work to do that copy, so you want to do it as infrequently as you possibly can. So when you've gotten to the point that there were 10 things in the stack, yeah, go ahead and build a stack that's big enough to hold 20, and then the next time 40, and the next time 80, and the next time 160, because it'll mean you'll have to do these growing operations a lot less frequently. Okay, so to review, a stack can be implemented with a linked list. You could absolutely implement it such that you're putting in at the top and you're taking out of the top, and that's the easiest implementation with a linked list. You could also implement it such that you're adding and removing from the bottom of the linked list. That's okay, it works, it's just more work. You could also implement a stack using an array, which is what we're looking at here. In that case, the simplest idea is to put all new entries in at the back of the array, what I'm calling current entries here that you're keeping track of, where the most recent entry was placed. You could absolutely do it at the front, it's just more work. So doing it at the back, i.e. at the location current entries, is more efficient than doing it at the front if you're using an array. Are those your only choices? Absolutely not. You could also implement a stack using an array list, or just a list if you're over in C#. You could conceivably, you could conceivably implement a stack using a doubly linked list, which is not something that I spoke about in the previous lecture, but I'm just going to give you the high-level version of what a doubly linked list is. So up until now, when I talked about a list, I start off talking about the head of the list, or the front of the list, and I typically drew the list such that it was like this. And we called the node class, let me try that again. The node class was typically, and you have your curly brace, you had your int ID, which held the number that you're storing in there, and then you had a node called next. And that represented this pointer that we have here that connects each of the nodes to the next one. There's nothing that stops you from also having another, we'll call it pointer or connector called previous. And at that point, what you would have is a linked list that looks like this. Now, the advantage of this is that in general, with linked lists, it's very easy to do recursion to move your way down the list this direction. That's quite easy. We've seen examples of that where we did the search just a few moments ago. But if you ask me to find something at the very back of the list, or in any reason you need me to go this way, it's quite difficult to do that if you only have a singly linked list, i.e. you only have the nexts. If you also have the previous, then it's very easy to go backwards or forwards through the list. And you might say, why would you need to go backwards through the list? Well, let's imagine that I put all of the students in to a linked list as they're being enrolled at KSU. So each new student comes along, I stick a new entry at the end of the list. Well, let's imagine that somebody asked me to report on all the new students that were only added this semester. Well, how would I find them? If I start at the beginning of the list, I'd have to go all the way to the end to find the most recent person and then work my way backwards through the list, which would be very, very difficult to do. So that will be an example where you would want to make a doubly linked list where you have a next pointer and a previous pointer. The only thing that makes this work is that when you insert new nodes into the list, you have to connect all of the pointers or all of the links appropriately such that all of the various bits of the list are being connected together. So that's the idea of a doubly linked list. I will point out at this moment, you're probably saying, whoa, there's a whole lot of stuff going on here. And yes, there is. There is an entire class about this, which I mentioned before. I just want you to have a high-level understanding that linked lists exist. Basically, it's a set of nodes that are connected to each other. Typically, they would only be connected in one direction, and you would typically call that connector or that link next. It is possible to have a doubly linked list, in which case you will also have a previous, which you just connected at the time that you insert the node. That's really all I need you to get out of this idea of a doubly linked list. So, based on all of that, let's talk for just a moment about this word here, big O. And again, this is something that entire classes are about this topic. So I only want you to get a high-level understanding of this. Big O is the measure of how much work it is to do something in an algorithm. So any operation that you do in an algorithm is going to be considered one operation. And so let's take a look at our example that we had before I added all these previous pointers and all this nonsense in here. So we had this stack, and it had, at this moment in time, it has two things. I'll just erase the guy who's not connected over here. So if I asked you, I want you to go through the list, and I want you to find for me if Paul is in this list, how would you do that? Well, you'd have to start off at the beginning. You would create some kind of temp pointer or link. You'd look to see if Paul is in this first node. If it's not, you would move temp down here, and you'd look to see if Paul is in here. If it's not, you would move temp down here, and you would keep going through the list until temp is pointed to null. At that point, if you haven't found Paul, he's not in the list. So you know that there is no Paul, and you would return false. If you did find him at any point, you return true, or you return his name, or whatever it is you were supposed to return. So my question to you is, how much work is it to find or search for Paul? Well, the answer to that question is not as simple to answer as you might think, because in this case, it looks like it took me one operation to make this pointer or this link, and then it took another operation to move it, and a third operation to move it again. So that's 3 there. When it was up here, I had to check, is this equal to Paul? So that was one operation. When it was here, I had to check if this was equal to Paul. So that was another operation. And when I got to here, I had to check if this was null. So that's another operation. So it looks to me like I did 6 total operations in order to figure out whether Paul was in this list. Is it always going to take 6? No, it's not. If this list was much larger, like for example, if there was 1,000 entries in the list, then it would have taken somewhere around 3,000 operations in order to see if Paul is in the list. It grows linearly with the size of the list. The more entries that are in the list, the more operations that I will have to do. So if you were asking me, what is the efficiency of doing this search operation on a linked list? The answer is, it depends on the size of the list, which is not a very satisfying answer. So just like in algebra, where you have a variable that represents the size of something, or an unknown effectively, you might say 2x, where x is some value that you will fill in later. In big O notation, we would say n is the size of the list. So how many operations will it take for me to search through the list? Well, it looks like it took 6 to go through 2, so it seems like the answer is it'll take 3n to find whether something is in the list or not. That's very accurate, sort of, but it's also unnecessarily complex. The 3 really doesn't matter in the grand scheme of things, because if there are 100 entries in the list and you ask me to find something, then it takes about 300 operations. If there are 1,000,000 entries in the list, it's going to take about 3,000,000. What's more significant, the fact that it was 1 versus 1,000,000, or the fact that it was 3 versus 3,000,000? Well, the 3 doesn't really matter. It's the million that matters. So when we speak about big O, we would say the order notation of searching for an item in a list is what's considered order n. Because effectively, I'm going to have to do something that's going to grow linearly with the size of the list. If you do it in an array, you would also have some amount, a very similar order n. In order to go through the array, I'd have to look at every single item in there, and depending on how big the array is, that's going to tell me how many things I'm going to have to search. So searching in an array is also considered order n. You might say, well, then isn't everything order n? No, it's not. You're actually going to see in the next lecture that some things are better than order n. You might be able to find things faster than you would looking for them in a linked list or in an array. So there is no one right answer with data structures. I need you to think through this for just a moment with me. When somebody says, I need you to store this information, if you're working at a job, they're not going to tell you, I specifically need you to store it in a linked list where you have this and this and this and this. They're mostly going to leave it up to you to decide how to store it. What's the most efficient way to store it? And what you're going to need to understand is, how is somebody going to eventually use this structure that you're putting stuff in there? Are they going to need to search through it? Are they going to need to sort the information in there? Are they going to only insert and delete at the top, like when we're doing with a stack? All of those things radically change how much work it is. So let's take our stack example and let's talk about this big O thing that we were talking about, which again is a measure of how much work doing stuff is in your algorithm using your data structure. So when we had our stack here, assuming that we implemented it such that we are always adding new nodes to the top and we are always removing nodes from the top, then how much work is it for us to put an entry in or take an entry out? Is it n? Is it affected by the size of the current stack? No, it's not. That's the beauty of doing all of this work at the top. Because I'm doing it at the top, it is actually only going to be one operation to put the node in there, and it's going to be one operation to take the node out of there. Now again, you might say it's not one, it's actually going to be create the new node, set the next pointer to the top of the list, and update the top pointer. It looks like it's really actually 3 operations to do a push and 3 operations to do a pop, but it's always 3. No matter how many nodes are in my list, even if there's 1,000,000 in here, it doesn't matter, it's still going to always take 3. So when we write this in order notation, we say that it's an order 1 operation. And the reason we say order 1 is because with big O notation, we always drop any constants. So the actual answer was 3, sort of, but we decide that we're always going to report that as order 1. I know this is all very confusing, but you can probably see immediately, without thinking too much about stuff, that when we were looking at this first chart, I said that in searching throughout this list was always going to be order n. So if there's a million items in here, it'll take a million operations. Versus doing the stack that we were just looking at, the stack is order one, no matter what. So it is much, much, much more efficient, even if we have large amounts of data, to work in a stack than it is to search a linked list. And that's really the whole point of Big O. It's a way of saying what is more efficient than what. Which thing is going to be faster than something else? The actual speed at which it takes to search a linked list with a million items is going to be dependent on a lot of factors. How fast is your computer? What else is it doing? Is it running any other things? So the actual number of milliseconds or microseconds that it takes for it to actually do that operation will vary from time to time. But the size of the list is what's actually going to make it vary more. It may be that sometimes a million is the same speed as a million and five. It may be that sometimes a million 10 runs faster than a million because the machine was doing less other work and therefore you got a faster action. But what will always be true is that searching a linked list with a billion items will be 10 times more work than searching a list with a million items. That's totally not true because a billion is more than 10 times a million. It'll be 1,000 times more work than searching a list with a million. 1 billion is 1,000 million. That's why I got confused. So what matters is that the n is what differentiates how much time it takes. So that's what I want you to get out of Big O notation. It's a measure of can you do it very quickly, which this is an example of doing it very quickly. Order one is the best case scenario. You will always be able to do it in effectively one operation. You just make a node and shove it at the front. Whereas searching a linked list or searching an array, it varies depending on how many items are in the linked list or in the array, and therefore you would say that that is order n, depending on how big it is. So that's a brief introduction to the concept of Big O. I don't need you to understand everything about Big O because, again, there are entire classes where they will talk about this later on in your career, and you will learn a lot more about Big O. But I do want you to be aware of the basic idea, and there could be a question on the final about asking you, from a Big O standpoint, which of these is more efficient or less efficient. So I need you to have a decent understanding of what that means. Okay, this last slide here shows you another implementation of a stack in C#. And instead of using what I used, which was a linked list in my code, or instead of using an array, which is what I showed you when we were drawing on the little whiteboardy thing, in this case they used a list, which is a built-in type in C#. And this is very like an array list that we have over in Java, except in C# it allows you to specify the object type, much like the array list does in Java, for what it is that you want to put in the list. So in both of these cases, what we're doing is we're just adding a new item to the list. When you want to push something in, you're calling the add method. When you want to take something out, you can address the list as if it were an array. That's one of the nice features in C#. In Java, you'll do get at, and you can certainly return whatever you get. There's also a remove at position, which allows you to pull something out. So this is just another implementation. All right, so before I move on to the next part of this lecture, I need you to review the following things. A stack. I want you to immediately picture pancakes when anybody says stack. And I want you to remember that when you take a pancake off, it goes on the plate. The next one goes on top of that, the next one goes on top of that, the next one goes on top of that. And when you start eating, you eat from the top down. So the last pancake that was made is the first pancake that was consumed. You can implement a stack using a linked list where you insert it at the top of the list or at the bottom, but it's better at the top because it's easier. You can insert it in an array. You can insert at the front or the back of the array. It's easier to use the back of the array because it's easier. You can use a list or an array list, or you could do other things. There's no reason that it has to be one of these. You can implement it however you might want to implement it, so long as last in, first out. That's the most important part of a stack. So that's the idea of a stack. I will mention one final thing about a stack. When we spoke about recursion, and when we spoke about one method calling another method, we often talked about the execution stack, which is a similar idea. It's a stack where your main program is at the bottom, and when it calls a method, that method gets layered on top, and then it executes, and when it's done, it goes away and you're back to the bottom. If a method calls another method, which calls another method, which calls another method, it's always the one at the top which is executing. Why? Because the execution stack is a stack. Also, it is the case that the stack can overflow. Remember what I meant by that? If you have a limit on how much stuff you can stick in there, which in the case of my array, it was set to be 10 and I tried to insert the 11th thing, that's a stack overflow. In the case of the execution stack, you have a set amount of memory in your machine. Actually, you have a set amount of memory for your Java virtual machine or your C#. But either way, there is a set amount of memory that is allocated to the execution stack. If you have infinite recursion, where the recursion is calling itself over and over again because you didn't write a good base condition or something went awry, you can actually overflow the stack because you keep adding more and more entries in there until you run your machine out of memory, at which point you will get the actual error, stack overflow error. And that's because, again, you ran yourself out of memory. So that's an aside. I just want you to realize that stacks are really used in computer science all over the place. As a matter of fact, you have been using stacks since the very first program you ever wrote. You just really never knew about it. It's how all of those methods call and execute. The one on the top is the only one that's ever executing, much like only non-barbarians eat the first pancake from the top of the stack. All right, moving on. You're always going to have push, pop, peek. You might have an empty, which tells you whether it's empty, and you'll probably have some form of a stack or some form of a search. All right, so the next topic we're going to talk about is what's called a queue. So unlike stacks, where I want you to think about pancakes, for queues, what I want you to think about is the Chick-fil-A in the Student Center. When you go and you place your order, you have to get into a queue in order to get your food. Theoretically, the first person in queue is the first person to get their Chick-fil-A. The last person into the queue is the last person to get fed. We are not going to debate the wonders of the Chick-fil-A. We are not going to debate whether it is always actually executed that way. But in theory, the first person in the queue is the first person to be served. This is true when you call into customer support on some phone number. You are supposedly answered in the order in which you were received. When you are getting to the grocery store and you're trying to check out, you are executed in the order in which you come in. Hopefully you're not actually executed, because that would be terrible in a grocery store. Although the way grocery stores are. Anyway, moving on. All right, so queues are implementations of first in, first out. The last one that we spoke about, which were stacks, were last in, first out. Very different. LIFO versus FIFO, which is first in, first out. All right, in a stack, we talked about push and pop. Those are typically the verbs that are used for interacting with a stack because they make sense. You're pushing things in and you're popping things out. In a queue, because you're not doing exactly the same thing, we use the terms in queue and dequeue. When you are done with your grocery shopping, you in-queue yourself into the line for a checkout, and when you get to the front of said queue, you are dequeued and checked out. There's a lot of metaphors in here, but anyway, moving on. So in-queuing and dequeuing are the verbs that we tend to use. You may see a peek because it may be useful to see who is the next person to be executed, and so on and so forth. But in-queue and dequeue are the verbs that we're going to use here. So drawing this out in a picture, I want you to look at the implementation. In the case of the stack, you notice that everything happens on one side. Whether that side be the front or the back or the top or the bottom doesn't matter, but all the pushes and all the pops are happening on one side. In the queue, you will notice that they are happening on opposite sides. The new people go in on one side, the next person to be dealt with is pulled out on the other side. So again, it could be implemented either way, where front and rear are reversed. All that really matters is that you're in-queuing and dequeuing from opposite sides of the data structure. So here's an implementation of a queue, and we have an in-queue and a dequeue. This is again being done with a linked list. I didn't bother to re-implement this for you. You can absolutely copy this and paste it yourself. You see that we have a peek method, which simply returns head, which again is the front of the list's ID. We have an in-queue method, which we are going to put in at the front of the list. And then we have a I'm sorry, I said that backwards, and that's why I paused. Sorry, we are in-queuing at the back of the linked list in this code, because I was actually reading the code and figuring out what it was doing, and we are going to dequeue from the front of the linked list, which is also why peak is looking at the front. That should have been a clue. All right, so in-queue is in-queuing at the back of the linked list. If the list is currently empty, then we know that the head is going to point to the new node that we're putting in. We stick all the data in the node, and we set head pointed to it. That means we now have a list with one item in it. If it is not, then we are going to walk our way down until the tail pointer is pointed to null. When the tail pointer is pointed to null, we're going to instead change that to tails next equals to the new node, which is going to insert it at the end, and then we're going to update tail to point to that node. Okay, now you might be thinking to yourself, what is tail and where did it come from? Which is also what I'm thinking, because it's the first time it was ever mentioned. These are not the greatest slides. Okay, when you create a linked list, we have talked about head. Head is wonderful. It's the thing at the front, and it points to this happy little list all the way over here. Okay, you put your numbers into the list or whatever data you're going to store in there. That's all makes sense. So hopefully none of that is new. The other thing that is often done is that you maintain another link or pointer, which we call tail. And it always is going to be linked to the last node in the list. There's nothing magical about tail, just like there's nothing magical about head. The tail pointer is going to be updated only when you add in a new entry into the list. So if you're always going to add at the back of the list, then you can simply say tail up, or tail.next is going to get a new node. You're going to put whatever data in there, and then you're going to change tail to be tail.next, which has the effect of the tail pointer always pointing to the right place. Okay, if you always do this, it just makes it so that you don't always have to start off at head and work your way down the list until you find the appropriate place, which is just a lot more work. The tail pointer just gives you immediate access to the back of the list so that you can throw new things in there. It's very helpful when you're dealing with a queue, which is what you're dealing with here. So to be clear, if this is an implementation of a queue, then effectively the order in which people are processed will be like this. The first person to be processed will be this person, the second will be this, the third will be that, and this will be the last person to be processed because, well, they were the most recent person to be put in. All right, so you will dequeue off of the front and you will in-queue onto the end using that tail pointer. All right, so that is a queue. So which data structure would you pick to implement a queue? Why? In making your choice, consider the data structure, which orientation you're doing, front or back. Is there a resizing overhead? And what's the big O of all of that? So your choices were doubly linked lists, arrays, singly linked lists. So what we have looked at so far is a singly linked list. And in the circumstance where we are in-queuing at the back and we have a tail pointer, this is order one. It only takes one operation to do an in-queue for a singly linked list. Likewise, it only takes one operation to do a dequeue for a singly linked list because you just take it straight off the front of the list. If you reverse things and you in-queue at the front and dequeue at the back, as long as you still have your head and tail pointers, it's actually no worse. You'll just dequeue off the tail and you'll in-queue at the head. Works just the same amount of effort either way. Okay, is there a resizing overhead with a singly linked list? And the answer to that is no. The nice things about linked lists is that they dynamically grow and shrink as you get entries in and take things out. So our queue never has to change. We never at any moment have to say, oopsies, we're about to insert one too many, now we have to go resize the entire thing. So singly linked lists will have a big O of order 1 for in-queue, order 1 for dequeue, provided that you have a head and tail pointer. There is no resizing overhead, and it actually does not matter the orientation as to whether you work at the front or the back. A doubly linked list all works the same way. There's actually no advantage for a queue to doing a doubly linked list. It's the same as a singly linked list. You just got all these extra pointers which you have to maintain, but it's very, very doable. It'll still be order 1, and order 1, there's no resizing overhead, and the orientation still does not matter. Okay, so let's talk about implementing a queue in an array. All right, so a picture would probably be worth 1,000 of my words here. So I'm going to give you an array. I'm going to give you 10 cells. This is cell 0, 1, 2, 3, 4, 5, 6, 7, 8. 10 cells. Oh no, there was 10 cells. There were 0 to 9. Ugh. What was I thinking? All right, there we go. Okay, so if we are going to implement a queue here, how would we do it? Well, presuming that we still have my magical current entries, current entries is currently going to be equal to 0. All right, so where are we going to stick the first person? Well, my guess would be that you're going to stick them in here. So this is not really very controversial. Enda is going to get added to cell 0. That will be true regardless of whether we consider this the front or the back. So the question is, when you go to insert the next person, where are you going to put them? So at this point, current entries is equal to 1 because I have actually added one person into the list. All right, if I in-queue the next person in here into cell number 1, that works, but there might be a bit of an issue here. When I go to dequeue the first person, I will have to shuffle everybody over one cell to the left, because when I dequeue, I'm going to dequeue out of cell 0, and then I have to move everybody all the way down the list, however many of them there may be, so that the first person is back in cell 0, the first person to be dequeued. If I do it the other way around, then the new person would go into cell 0, and then I have to move Enda to cell 1, which means that I would have to move whoever's in cell 1 to cell 2 and all the way down the list. So it seems like with a linked list, there's an immediate problem. No matter which direction that I try to do it, and to be clear, what I mean by direction or the orientation here is, are new people added after? Meaning, if this is cell 0, does the next person go into cell 1? Or does the next person go into cell 0 and I move everybody down? If the next person goes into cell 0 and I move everybody down, my in-queue is going to be order n instead of order 1. My dequeue is going to be order 1 because I can just take them right out at the front. If I do it the other way around, then my in-queue is going to be order 1, but my dequeue is going to be order n. So one way or the other, I'm going to have a lot of extra work that I'm going to have to do with an array. So you might say that for a linked list, for a queue, a linked list is going to be easier to implement just because of the nature of how you have a front and a back that immediately allows you to do things. There is a clever trick that you can use with an array, which is called a circular array. To be clear, there is no such thing as a circular array. But you see how I kept track of current entries? I can also keep track of first entry. All right, and what's happening here is, in the beginning, first entry, and I'm just going to clean up a lot of this crud, first entry and current entry immediately start off as being 0. All right, and life is good. I don't have anything in my array. All right, so I put my first person in, that's going to be Enda. All right, I'm going to change current entries to 1, and I'm going to leave first entry at 0. I'm going to put Fred in next. So Fred's going to get put into cell 1, and current entries is now 2, first entry is still 0. I'm going to add Jane. Jane goes into cell 2, so current entries is now 3. And now I'm going to dequeue. When I dequeue, I'm going to get back Enda because he was the first person put in, and dequeue is going to take him out of there, but at that moment I'm going to update first entry to be 1. So now my first entry is here, and my last entry, or the place that I'll put my next person, is here. So think of these as 2 links or 2 pointers that tell me which part of the array I'm currently using. The array is empty when first entry is equal to current entries, when the two have caught up to each other. I've dequeued everybody out of the queue and there's no one left in the queue, then my first entry and my current entries will be equal. When I put somebody new in, then my current entries is going to get further and further away. When I take somebody out, my first entry is going to move closer and closer to current entries. There is, of course, weirdness when you get to the end, because after you put in the 9th person, where does the next person go? Well, they actually go all the way back at the beginning, which is why it's called a circular array. I don't need you to spend too much time on this. I just want you to have an understanding that there is a clever way to solve this problem, which is a circular array. Overall, however, implementing a queue in an array is more painful than implementing it in a linked list, which is really why we taught you linked lists first, because it is possible to do it in an array, but it's not pretty. You're going to end up having to do this circular thing, or you're going to have to constantly shuffle everybody around in the array in order to make it so that it's correct all the time. Okay, and you could also do it in an array list, and the advantage of that is that it'll keep track of all of the array stuff for you. You just add and remove the appropriate entries as you go. So that's queues. This is the queue implemented as an array in Java, and that is the end of today's lecture. So let me review everything that we covered here very quickly from the standpoint of what is it that you need to know for a test. You need to understand what a linked list is. That was the last lecture. If you didn't understand that, please go back and rewatch the linked list lecture, because the next lecture is going to be even more confusing. So make sure you understand linked lists first. Linked lists are simply a node. It has some data. It has a next pointer. Maybe it has a previous pointer, and they connect to each other all the way down a big long list of nodes. The last one is always going to have a null. The first one may be a null if there's nothing in the list, and eventually it will point to a node which will connect to another node, which connects to another node, and so on. That's a linked list. You can implement, today's lecture is stacks and queues. You can implement a stack or a queue using a linked list. You can also implement stacks and queues using arrays or array lists or just lists. It is possible in all of the above. It'll work in all of the above. It's just how much effort is it to maintain the structure in a way that when you do a pop or a dequeue, do you have to shuffle things around inside the structure? And it is important to understand that that shuffling is actually work that has to be done, which makes the algorithm less efficient. So from an efficiency standpoint, putting things in and taking things out, you need to draw it out on a piece of paper and see how much work it is, just like I was doing on the little whiteboardy thing where I was moving things around and showing you. If you didn't get all of this, I would recommend rewatching this lecture, honestly, because there was a lot in here and there was a lot of different concepts that you've run around. We don't need you to know all of it. We're not asking you to implement all of it. We just want you to understand the ideas of how it all works and how it all connects to each other. So that's the end of today's lecture. There's going to be one more in the data structure section, which is really technically for next week, which is the week before Thanksgiving. But I'm going to go ahead and post it just so that you guys have the ability to move on. But this is the data that I need you to understand up to this point. I need you to understand the queues and the stacks before you move into the next lecture, which is going to expand in another direction. So hope you guys are doing well, and I will see you in the next lecture, which will be lecture 23. Thanks.